everyone, Grzegorz Baran here. Before we dive in, huge thanks to everyone who contributed to my research, especially those who responded to the LinkedIn surveys I published. Your input made the video sharper, clearer, and way more grounded. This video is all about UV unwrapping for hard surface assets, one of the most misunderstood but absolutely critical steps in 3D asset creation. It's not just a box to tick. UVs affect how textures look, how materials behave, and ultimately how your asset performs on screen. My goal is to unpack the logic behind UV unwrapping so everyone can make smarter choices and get clearer, more consistent results. Let's start with the basics. No matter how good your textures are, they're only as strong as your UVs. The unwrap is the invisible bridge between geometry and material. It decides what actually shows up on screen. For years, UV unwrapping felt like a gray zone to me. No clear rules, just inherited habits. And that's the problem. Repeated mistakes often get mistaken for best practices. So I went back to fundamentals, questioned my assumptions, dug into focused research, and this video is the result. It's not a checklist, it's a framework, a guide to why behind our UV decisions, why we place seams where we do, why certain patterns work better, and how to avoid common traps. UV unwrapping isn't just technical, it's actually a creative puzzle with real consequences. If I had to sum it all up in one line, UVs don't need to be perfect, they need to be functional. If your unwrap supports clean bakes, consistent textile density, and fast iteration, you are doing it right. Every 3D prop goes through 3 key stages before it reaches the game engine: modeling, UV unwrapping, and texturing. Each stage builds on the last, and they often overlap. If something goes wrong early on, it can ripple through the entire pipeline, affecting both visual quality and performance. Modeling gives us the geometry, the canvas, but to make textures and materials actually work, we need to define how they wrap around the canvas. That's where UV unwrapping comes in. And here's the thing. The same texture size when applied can look great or terrible depending on the quality of the UV layout. At the same performance cost, you can end up with either creep detail or blurry mess. A better UV layout means better textile density even with the same texture size. So what's the Texel then? Texel stands for texture pixel. Texel is calculated as texture resolution divided by object size, usually in pixels per meter or pixels per centimeter. So let's say you have 2K texture applied to a 2 meter large 3D object. That gives you 1024 pixels per meter. If you measure in centimeters, it's 2048 pixels divided by 200 centimeters, which gives you 10.24 pixels per centimeter. There is no universal textile density everyone should follow. It's defined per project based on screen resolution and viewing distances. The goal is to ensure that each screen pixel is matched by at least one texture pixel, and that's it. So typical values for first-person games are 1024 pixels per meter, for third-person games 512 pixels per meter, for top-down games 256 pixels per meter, but for example for movies, film or visual effects we go up to even 10,000 pixels per meter. Texel, while defined, must be consistent across the entire project. If textile density varies too much between assets, we get noticeable visual mismatch. Some things will look sharp while others blurry, and the whole scene would feel off. Textile density has too much expected screen coverage. A weapon in a first-person shooter that fills 25% of the screen needs higher textile density to some background prop that is meant to cover 5% of the screen and at most can get away with much less. Vista objects will need even lower texel density as they are barely visible by design. So when it comes to texel definition, we need to be sure that each asset receives the minimum required texel density to maintain visual fidelity without wasting resources. The texel doesn't need to be higher than what we will actually see on the screen. We just need one texture pixel to represent one screen pixel. Anything more should be considered as a waste of memory and resources that could be spent elsewhere. When we deal with large hero assets like weapons in first-person view or characters player interact with, and a single 2K texture isn't enough to achieve the desired texel density level, we either split the asset across multiple textures called UDIMs or switch to tileables. Tileable textures are exactly how we usually handle large surfaces like terrain, building walls, and floors. These are repetitive textures which allows us to tile them multiple times until we match the required texel. So when it comes to UV unwrapping strategy, there are two main directions we usually take. Tileable textures, which rely on repetition and masking. These are great for environments, props, and modular kits with the UV unwrap directionality. For such, seams minimization and UV island directionality are the key principles. And dedicated textures with their full control over texture authoring. These are ideal for hero assets, weapons, and characters. These allow for big detail and precise placement. This is the default assets texturing technique in Substance Painter. Other techniques like trim sheets, atlases, and UDIMs blend aspects of both. Shaders can add variation or help to blend layers dynamically. This guide focuses on dedicated textures, which are often the most challenging, but also the most rewarding from a UV unwrapping perspective. That doesn't mean that principles here don't apply to tileables, especially when you're aiming for a masking-friendly UV layout. But overall, tileables tend to be more forgiving during unwrapping. UV tile efficiency and baking issues are less of a concern for tileables, which come with their own challenges, like maintaining UV islands directionality and layout continuity. To really understand UV unwrapping, we need to break it down into its core building blocks. That means identifying the key principles behind three major categories: UV seam, UV islands, and UV tile organization. Once we clarify what drives each one, we can make informed decisions rooted in clear, consistent logic. Seam placement is flexible and context dependent. The goal is to balance shading fidelity, texture distortion, and unwrap efficiency. UV seams don't trigger draw calls. The GPU renders triangles individually either way. But UV seams do affect vertex count. Every time vertex has different UVs across a seam, it gets duplicated in the vertex buffer. That increases geometry size and therefore memory usage. In most cases, this isn't a major concern. The added memory is small compared to what textures consume. Saving on this makes sense only for less efficient platforms like mobile or VR, where every single kilobyte matters. So yes, more seams means more duplicated vertices and a higher memory footprint, but fewer seams come with trade-offs: more distortion, worse packing, and baking artifacts. That's why the real question is, where should we place seams and where should we avoid them? The goal isn't one island to rule them all, but rather strategic seam placement. So let's put together all key principles of seam placement. Visibility and logic comes at first. We should place seams in hidden or low visibility areas, or where they align with real-world seams or logical geometry transitions. This way we minimize distraction, as seams in high visibility areas can break immersion, especially on organic surfaces like faces or clothing. It also helps to preserve silhouette, as logical seam placement avoids disrupting the perceived shape or flow of the model. It also helps to support realism, as aligning seams with real-world about garment stitching, or panel breaks, or natural faults, reinforces believability. The next core principle is about angle-based seam placement. Technically, we can place a seam at any angle, but in practice, some angles are riskier than others, and knowing where to cut can make or break our shading. 0 to 30 degrees is the danger zone. These shallow angles usually represent smooth, continuous surfaces. Cutting here can introduce unwanted shading breaks and disrupt the visual flow of your model. Unless we have a very specific reason to cut here, we should avoid seams in this range. 30 to 60 degrees is the gray situational area. Seam placement here depends on your baking setup, shading model, and whether the surface is meant to look smooth or faceted. It's very contextual. Cutting at this angle should be tested, but can be assumed as acceptable. 60 to 80 degrees is in safer territory. These angles are steep enough to justify a shading break, but not so sharp that they waste UV space or stretch textures. Seams here are especially useful when paired with hard normals or subtle curvature transitions. They help preserve shading fidelity without compromising unwrap efficiency. Anything above 80 degrees angle is safe for UV cutting and even recommended for hard surface assets. These are our clean corners and hard edges. Cutting at these angles helps isolate shading discontinuities and prevents normal map artifacts. In hard surface workflows, this is a standard practice. The next good place for UV seam cuts are hard edges. While not all seams require a hard edge, every hard edge should have a seam. This helps to avoid shading artifacts and supports clean normal map baking. Basically, if we don't split the UVs at those edges, baked normal maps can bleed across them, causing shading artifacts. A seam allows the normal map to encode each face's direction cleanly, avoiding tangent space errors. From technical point of view, once a vertex is split, either by a hard edge or UV seam, it's duplicated in the vertex buffer. Stacking both doesn't add much extra cost beyond the first split, so pairing them is barely noticeable from the memory point of view. So always pair hard edges with UV seams, while for organic models, use seams where needed for distortion control. But keep normals smooth unless there's a visual reason to break them. Next are acute angles. If a part must be split, acute inside angles are often the safest choice. These areas, faults, creases, tight corners, already compress geometry, so adding a seam introduces less UV distortion. They are often shadowed or occluded, which makes seams less noticeable. And because surface curvature is low across these transitions, there's less risk of texture stretching or skewing during unwrapping. This approach also mirrors how real-world materials behave. Think of cloth folding or metal bending. Those transitions naturally happen at acute angles. Mimicking that in your UVs adds realism and helps texture behave more intuitively. We should avoid curved surface seams, especially on organic shapes unless necessarily. Curved seams can be visually disruptive. Such seams really catch the eye, especially on organic shapes like faces, limbs, creatures, where they often intersect smooth shading and natural flow, making them stand out unnaturally. These are especially noticeable under dynamic lighting or animation as they break visual silhouette continuity by interrupting the perceived form. Curved surfaces are harder to unwrap cleanly. Seams here often lead to stretching or compression, especially with high-frequency detail. Normal tangent space discontinuities across curved seams can cause visible shading glitches, particularly in real-time engines. Not to mention that it's quite challenging to paint across curved seams without visible mismatches. Sometimes curved seams are unavoidable, like around eyes, mouths, or joints. islands. In those cases, careful placement and padding in the UV layout can mitigate issues. If the curve is subtle and in low visibility area, like under the character's arm, the seam may be acceptable. When using triplanar mapping like the one Substance Painter offers, seam placement becomes more forgiving and overcutting is acceptable, especially if it improves texture space usage. Since triplanar projection blends textures based on word or object space normal, it bypasses traditional UV seams entirely, therefore allows for better island orientation. Basically, it frees us from visual seams constraints, allowing to freely rotate and even scale UV islands for optimal packing. With this approach, visual artifacts from seam placement are drastically reduced or eliminated. It's ideal approach for tiling or procedural materials. But if we switch to traditional UV-based painting later, those overcuts might become problematic. Also, if we use hand-painted masks or decals, UV seams still matter for precision. We should split UVs where different materials meet each other, especially reflective versus non-reflective, or where tinting masks require separation. This isn't a hard rule, but can be essential for baked workflows or texture-based blending. Splitting UVs help isolate shading models, as reflective surfaces often use different bidirectional reflectance distribution functions and require distinct normal map behavior. If we don't split UVs, tangent space continuity can cause shading artifacts where the material logic diverges. It's also critical for masking. When we use tinting masks, vertex color, or material ID maps, UV splits allow precise control over where each mask applies. We can also use seams for shading control. Strategic seam placement can help mitigate shading issues on low poly assets or where resolution constraints exist. It's all about tricking the light. When working with low poly models or limited texture resolution, shading artifacts like visible gradients or distortions can occur because the UV layout stretches or compresses texture data unevenly. By placing seams in areas where shading transitions naturally occur, like along hard edges or hidden parts of the model, we can reduce visible texture stretching. It allows for better normal map baking, since the tangent space can reset at seams, and overall control how light interacts with the surface, minimizing shading errors. This way, UV seams help to manage shading by breaking up problematic UV islands, especially in constrained scenarios. Next, let's take a look at principles that deal with the size and shape of UV islands. So basically, when it comes to size and shape of UV islands, we should always prefer larger islands, as they means fewer seams and easier packing. But we should split them when we need to reduce stretching or improve packing. So don't be afraid to break them up for better UV space efficiency and fit among other islands. Next is the Texel consistency. We should always do our best to maintain even Texel density level across the model wherever possible. To visualize such, we can use checker patterns or distortion heat maps to preview and correct Texel inconsistencies. That said, not all texture areas are equally important. Scaling up UVs for critical elements, even up to twice their original size, is still acceptable if it improves texture readability. Just don't go overboard. Texel consistency is a guideline, not a sacred rule. We should avoid excessive upscaling of UV islands, as these come at cost. If needed, we should rather rearrange seams and optimize the layout to make more space, while keeping Texel variation within reasonable limits. It's perfectly fine to increase Texel density in areas that are close to the player or carry high visual importance. Likewise, it's smart to reduce it in hidden or peripheral regions, places that are rarely seen or don't contribute much to the overall visual impact. Straightening curved UV islands can significantly improve packing efficiency. While this often introduces some distortion, the trade-off is usually worth it. Straightened islands are easier to fit, faster to pack, and simpler to pad. In many cases, even with noticeable stretching or texel mismatch, the overall gain in texture space usage makes it a smart compromise. Stretching, unless we're dealing with highly directional textures, can often be compensated by higher texture resolution gained through a more efficient UV layout. In other words, it's usually worth accepting some distortion if it means that we can pack UVs better and get more texel density where it matters. In practice, especially when working in tools like Substance Painter, with this approach, even significant stretching is often tolerable, as long as the texture resolution is high enough to preserve visual quality. Whenever possible, UV islands, and especially seam edges, should be aligned horizontally or vertically. That's because 2D textures are made of square pixels arranged in rows and columns. When seams are angled or curved, they become less space efficient and require extra padding to avoid bleeding across edges. Misaligned seams also introduce the risk of visible jagged edges or texel artifacts, especially in low-resolution areas or along sharp transitions. Be especially careful with distortion in areas that use directional patterns, text, or high-contrast elements. These are far less forgiving. Textures like stripes, grids, wood grain, or brushed metal tend to exaggerate even small UV stretching or rotation errors. And any misalignment or warping of text like logos, labels, or signage is instantly noticeable and breaks immersion. Sharp transitions in color or value, like black to white or red to yellow, also make seam stretching and compression much more visible. In these cases, preserving directional integrity may require adding more seams or relaxing island angles, even if it means sacrificing some packing efficiency. Organic forms, especially skinned models, can tolerate more UV distortion. That's because their textures are usually more blended, less precise, and often deform in motion. In contrast, hard surfaces and tileable materials require much stricter UV control. You need clean alignment, minimal stretching, and consistent textile flow to preserve detail and avoid visible repetition. The tolerance for distortion is fundamentally different because each surface type interacts with lighting, animation, and texture detail in its own way. When working with trim sheets or tileable textures, it's important to align your UV's edges to the grid. This ensures clean texture flow, sharp transitions, and predictable reuse. Grid alignment helps prevent visible misalignments and makes it easier to snap UVs to consistent textile boundaries. It's critical for modularity and efficient asset creation. It also simplifies iteration and reduces texture waste across multiple assets. Now let's dive into the third set of principles, how we organize UV islands across the texture space. This part is all about structure, efficiency, and readability. Organize your UV islands by material type, shader assignment, or functional grouping. Avoid random scattering. It makes 2D editing easier and helps minimize visual texture bleeding. Why? Because grouped islands allow for targeted edits in tools like Photoshop or Substance Painter. They make masking and isolating areas for baking or painting much simpler. And when something goes wrong, it's easier to debug without hunting across scattered shells. Clean organization also improves readability and makes collaboration smoother across teams. Every texture pixel comes at memory cost, so efficient packing is a must. Maximize your texture coverage by aiming for 85 to 90% usage per UV tile. This gives you optimal textile density without risking texture bleed. Going about 90% is possible, but only if your padding is tightly controlled. On the other hand, anything below 80% is considered inefficient, since it wastes valuable texture space and reduces overall resolution. Regarding the padding strategy, follow general padding rules and adjust your padding distances based on MIP levels and the contrast between adjacent UV areas. Avoid excessive padding unless it's needed for baking. Here are some safe padding guidelines to follow. Padding distance can be reduced in low contrast areas, especially those that are rarely seen or viewed from a distance, since bleeding is less likely to be noticeable. Proper padding prevents texture bleeding during MIB mapping and compression. By following resolution-based guidelines and adjusting for contrast, you get clean, efficient results without wasting texture space. Consider overlapping of identical parts like bolts, screws, or repeating details, and consider mirroring symmetrical or opposite elements such as arms or ears, especially if they are rarely visible at the same time in gameplay or presentation. This is a simple and effective way to conserve UV space and significantly boost textile density without any noticeable visual compromise. Just make sure to separate overlapping shells during baking to avoid projection artifacts or normal map errors. Maintain consistent UV island orientation for areas with directional textures, like labels, text, stitches, or decals. If islands are rotated inconsistently, these patterns can appear misaligned, upside down, or sideways on the model. Keeping UVs aligned, typically with a consistent vertical or horizontal axis, ensures that directional elements follow a coherent flow across the mesh. It also makes painting and projection easier in tools like Substance Painter or Photoshop. Misaligned islands can cause confusion, break visual continuity, and often require tedious manual correction. Use heat maps, checker patterns, and other visualization tools to identify and fix UV problem areas. Clean UVs lead to better textures fidelity, fewer baking artifacts, and more predictable results in tools like Substance Painter, Photoshop, or engine shaders. These visual aids turn invisible issues like stretching, misalignment, or textile inconsistency into visible ones, making them essential for any serious asset pipeline. Avoid auto-unwrapping clutter. Excessive auto-generated seams can lead to visual clutter, memory overhead, and wasted texture space. That doesn't mean auto-unwrapping is bad, but it needs to be kept organized and under control. Automated unwraps often produce fragmented UV islands and too many seams, which makes manual editing harder, reduces packing efficiency, and lowers textile density across the layout. Most auto-unwrap passes benefit from a manual pass to introduce UV layout rearrangements, tweaks, islands merges, and overall manual cleaning up of necessary seams. Auto-unwrapping should be seen as a powerful starting point, not as a final solution. We can guide it by defining UV subgroups, setting constraints, locking critical components, and specifying desired flow directions. These steps help the algorithm make smarter decisions and reduce cleanup time later. When it comes to baking layout, we should avoid overlapping UVs when baking normal, ambient occlusion, or curvature maps. Overlapping shells can cause polluted bake results, where shading data from one part of the mesh bleeds into another, creating visible artifacts. To prevent this, isolate mirrored or stacked elements before baking. Once the maps are clean, you can reapply the overlaps to save UV space and boost textile density without compromising quality. UV unwrapping starts in the modeling phase. Good topology and clean geometry flow make the UV process smoother, more predictable, and easier to control. Always ask yourself, how would this be built in the real world? That mindset helps you place seams where they make sense, both visually and technically. Remember, this isn't a checklist to follow blindly. Every asset is different and context always matters. Use your judgment, bend the rules when needed, and aim for what makes the most sense for your workflow and final result. And don't get stuck chasing the perfect UV unwrap, it doesn't exist. There's always a good enough point, but this point should be really high, somewhere around 95% of what's possible. Hold your quality bar there, and always do your best to solve the UV puzzle as cleanly and efficiently as you can. Just don't let yourself spiral into an endless loop of second guessing. Sloppy UVs with low textile density lead to glitchy, blurry, or distorted textures. Good textile density means clean bakes, sharp detail, and fewer headaches down the line. Most problems only show up when textile density drops too low, during optimization, when MIB maps kick in, or when textures are viewed up close. That's when seams start bleeding. details get crushed and compression artifacts creep in. And suddenly, all those UV rules start to matter. Bad UVs also slow down iteration. They break masks, confuse texture painters, and make debugging harder. They waste texture space, inflate memory usage, and reduce visual quality, especially in modular and shared texture setups. In short, bad UVs cost time, performance, and polish. Good UVs aren't just cleaner, they're cheaper. UV unwrapping can be quick and painless for simple assets, but as complexity grows, it quickly becomes a challenge. In extreme cases, it can take days or even weeks if you're relying solely on native tools. And that's where dedicated UV tooling really starts to shine. Most 3D apps come with built-in UV editors. Some are better than others, but none are perfect. That's why most professionals enhance them with additional plugins, scripts, or replace them completely with external applications tailored specifically for UV work. These tools can dramatically improve both the quality of our unwraps and the speed of our workflow. Personally, I use Rhizome UV as part of my everyday pipeline. It's a standalone app with strong manual and automated features, with support for trim sheets, grouping, and which provides solid output quality. It's not tied to any specific 3D app, so once you learned it, you can use it across Blender, Max, Maya, whatever you prefer. I hope to cover it in more detail in a dedicated video soon, so I will keep it brief here. Just keep in mind, even with great tools, UV unwrapping is still a puzzle. Every asset is unique and very context dependent, but with a little bit of experience, the right mindset and the right tools, it becomes manageable, even enjoyable. Now let's wrap it all up. UV unwrapping isn't about chasing perfection. It's about making smart, informed decisions. There are 3 core pillars to UV unwrapping: UV seam placement, UV island size and shape, and UV tile organization. When it comes to seam placement, it's all about context. Cut where it makes sense. Hidden areas, hard edges, steep angles, or materials transitions. Avoid shallow cuts and curved seams unless you've got a solid reason. And always pair hard edges with UV splits to avoid shading glitches. UV island size and shape? Bigger is better, until it's not. Larger islands means fewer seams and easier painting, but don't be afraid to break them up if it helps with packing or distortion. Keep texel density consistent, but prioritize resolution when it counts, like close-up details or hero assets. Straightening curved islands might introduce stretch, but it often boosts packing efficiency. And unless you're working with directional textures, a bit of distortion is usually a fair trade for better texel coverage. UV tile organization? Structure is everything. Group islands by material or function, aim for 85 to 90% tile usage. Below 80% is wasteful, above 90% is risky, unless padding is tight. Use overlaps and mirroring smartly, but separate them before baking. And keep directional textures aligned, labels, stitches, decals. They all need consistent orientation. And debug early, iterate smart. Use checker maps and distortion heat maps to catch up issues before they bite you. Auto unwrapping is a great starting point, but always clean it up. Guide the algorithm, merge islands and remove clutter. And when baking, isolate overlaps to avoid polluted results. Mindset matters. Good UVs start with good modeling. Think like a builder. How would this be made in the real world? This mindset helps you place seams where they make sense, visually and technically. And don't get stuck chasing the perfect unwrap. It doesn't exist. Aim for 95 quality, call it done, and move on. Tools help, but they don't think for you. Native UV editors are fine, but native tools expansions or dedicated external UV tools can seriously speed things up and improve quality. But even with great tools, UVs are still a puzzle. You solve it with experience, judgment, and clear goal, texel efficiency. So yeah, UVs aren't just technical, they're strategic. Every seam, every island, every layer choice, it all adds up to performance, polish, and production speed. So make smart cuts, pack with purpose, and know when to stop. Thanks for watching. If you found this video useful, drop a comment, like, share it with your team, and stay tuned. Thanks to everyone who did it already. You're awesome. So, see you all in the next one. Cheers!